For joining us. My name is John Conway. I am the automation sales manager here in Buffalo, Western New York. And this is first in a series of tech tours that we're going to be doing in May. We're pretty excited about that. Again, a lot of you in this environment of today's world, we are working virtual, and we are trying to do subject matters and of interest. And if any of our clients have any requests on things that they want us to cover at future tech tours, please send it to myself or your account manager or one of our specialists. We appreciate that. We'd want to present stuff that you find meaningful and helpful. So today we're fortunate to have Chris Ryan, who's one of our newer automation specialists. Chris has a background in mechatronics. He is our sensor and safety specialist. Today he's going to be talking about the Rockwell Odos SwiftE reconfigurable 3D sensor or camera. Most of the applications tend to center around palletizing, case packing, and just completeness when you're checking shipping. So it's pretty neat product. Chris is going to go into pretty big detail on it. But just some housekeeping. I ask that all of you mute yourself, or I'll be muting you, so we can get through it. If you have any questions while he's presenting, please put them in the chat area, and we'll address them at the end. And then we'll also be open. We'll let you unmute yourselves and ask questions at the end. We have it slated to go a full hour. I don't think we'll go that long. It'll probably be under that, depending, again, how many questions. So with that, I'm going to turn it over to, again, Chris Ryan. Thanks, Chris.
All right, John, thank you for that introduction, and thank you, everyone, for attending today. My name is Christopher Ryan. I'll be your presenter. I'm an automation specialist with Rexel. I support the safety, sensors, and connectivity product segment of the Allen Bradley portfolio, as well as the industrial control and motion segments. So I want to start with why we are talking about a new smart product like this. Industry is evolving. The expectation of consumers is more personalization of the products they acquire. This is driving end users to create a higher number of products they use. So in itself, it creates an additional need for more flexible manufacturing. Where before end users would do switchovers of production lines once a week or once every few days, we have customers who do switchovers several times a day. So this is driving for new needs in smart sensing. To truly be considered smart, a simple discrete or analog connection to the control system is insufficient. The sensor must be able to communicate more information than the simple traditional connections allow. Rockwell Automation accomplishes this necessary communication utilizing two information-enabling technologies. One is Ethernet IP, which is now incorporated into higher-end sensors such as encoders, RFID transceivers, and code readers, as well as the new 3D sensor we'll be talking about today. So that's where this fits into the Rockwell Smart Sensors portfolio. The other information-enabling technology is IO-Link. Rockwell offers a wide variety of sensors on IO-Link, including proximity, photoelectric, temperature, and pressure sensors. Rockwell has a distinct advantage in utilizing IO-Link because it's the only company that offers controllers, IO-Link masters, and IO-Link sensors. This enables Rockwell Automation to deliver a superior integration experience. Many mundane applications are either ignored or rely on complex or expensive or both approaches to solve often basic questions needed to be answered about products, equipment, or parts. So this is a recent evolution of an existing technology. One of them is using light to measure distance. This is a very well-known technique. For example, a laser beam can be emitted, and the reflection from the surface helps us measure the distance to the object. For example, the Allen Bradley 45 DMS uses time of flight sensing, the laser distance measurement sensor. Now imagine if we could do that with 300,000 beams at the same time, covering a big area rather than a single spot. This is done through a new kind of sensor called SwiftE. SwiftE produces an infrared light that is invisible to the eye. It's projected over an area to monitor. This illumination and the sensor are co-located in the same device, so there's no external illumination unit required. The light is then reflected from the target object and each pixel independently collects reflected light. The time that it took for the light to come back to the device is calculated. This allows to calculate distance to each one of those pixels. That produces a raw image called point cloud. Point cloud is not very useful by itself. The user needs to make decisions based on the information. So we created the concept of virtual sensing zones, VSZs. A defined area the user can draw in a configuration and allows them to measure distance for height within that particular selected area. For example, the picture of the pack on the right hand, you can see there are several packets of meat that are particularly hard to measure because they have a film on top. Number 2, because the label could be in different places. And number 3, because the meat could be in different places. Yet with SwiftE, we can very accurately identify that there's one packet left out in the top left corner. And by measuring the distance, the height in this case, of the packages, we can clearly identify using 3D that the package is missing. Some considerations are some of the same considerations you'll see for any photoelectric sensor. Certain targets are difficult to reflect light off of, such as curved shapes, translucent materials, shiny spoons, or very dark materials that could absorb too much light. However, having the ability to average the readings off of many readings off of a single target gives us a much more reliable measurement in these cases. So at release, SwiftE that is available right now for customers is going to produce measurements of distance or height for each one of the virtual sensors created by the user. The user can create up to 64 different virtual sensors for any given sensing area, and then save up to 255 different configurations of virtual sensors. We call them templates. These virtual sensing zones allow the user to do applications like identification of missing or misplaced product, layering validation for pallets, for example, filling validation or rough measurements. One thing to have in consideration is the measurement precision is limited to 1 centimeter. This is not a high accuracy measurement device, this is a validation device. The difference between measuring distance and measuring height is really only if there's a background or not. In the image on the left, you see the object, and if we have a reference background, we can calculate the height of the object. But if there's no reference background, we can simply measure the distance from the device to the object. This is SwiftE. We're calling it a configurable 3D sensor. There's no additional software needed to configure it. It deploys with Ethernet IP connectivity to connect with Logix controllers. It produces a high-density sensor frame of 640 by 480 pixels with a field of view of 43 degrees by 33 degrees. It maximizes detection at longer ranges. The use range of the device is about 0.5 meter to 6 meters, or about 2 feet to 20 feet high. The illumination is infrared, so it's quite impervious to ambient lighting, and it's factory calibrated, ready to use out of the box. To configure this device, we use an embedded web application that's inside the device. The user will connect to the device, open the web page, and set up the configuration. Once the configuration is saved, then the device establishes a connection with the Logix controller, and through the Logix controller, obtains information about the virtual sensing zones produced in the device. So it's extremely easy to configure this application. Basically, when you open the web page, you have the capability to adjust parameters like illumination, and you're going to draw the virtual sensors, you're going to activate them, validate they are measuring properly, and then save your template. And then from the PLC, the user will just call the template number. And with the template number, they'll trigger measurement, and up to 64 virtual sensors can be created for any given template. Up to 255 different templates can be saved. The data then in Studio 5000 shows up as an input and an output assembly. In the input assembly, there's information about what template is in use, how many virtual sensors are in that template. And for example, any given template, you can see information about the data, which is the actual measurement, and the status, if it's used or not in that template, type of measurement being distance or height. There's no need to download an add-on profile or set up anything special to add this to Studio 5000. You just upload the EDS file or the electronic data sheet that's embedded in the device. That's all it takes. So before I show you how to upload the EDS file, I'm going to show you the device. Okay, everybody see my camera? I'll assume you can. You're all on mute. All right, so this is SwiftE
we see you, yes.
device here. Thank you. These are the 300,000 beams coming at the end. There's a optional mounting plate here that attaches to the device with 4 screws. It accepts a 1/4 inch by 20 threads per inch standard mounting for a camera tripod. On the back here, you'll see the connections. We have 2 M12 connections. One is a 4-pin M12 for power. The power requirements are 12 volts DC, 30 watts peak, 60 watts peak, 30 watts typical. The second M12 connection is an 8-pin that is not used. It is reserved for future revisions. And then we have an RJ45 connection for Ethernet. So that's all it takes is these 2 connections here. I'm going to attach this to the edge of my desk so we can look down at some targets. For reference, the top of my desk to the floor is about 29 inches. And I'll show you the targets we'll be looking at. So we'll be looking at what's inside of this box. This is your standard Rexel shipping box. And we'll be looking at some Allen Bradley industrial components that are inside that box. So we'll see what that looks like inside the camera. I just wanted you to see what that looks like. Not from the point cloud. Okay, so from here, we're going to go upload the EDS file. You can use RS Links Classic, or you can use Factory Talk Links Browser. So what we're going to do is you just expand the Ethernet IP network here. RS Links Classic will automatically upload the EDS file for you. However, you can right-click the device and click Upload EDS File. Also, you can download the EDS file from the Rockwell Product Compatibility and Download Center, or PCDC as they call it. In RS Links, you can also right-click the device and click Module Configuration. From here, you can change the IP address. Once you load a different IP address, you'll see an alert saying the device is a pending address change and requires a reset. To change the IP address in RS Links, you need to make sure that the device is either not connected to a controller, or if it is declared in the I/O tree of a controller that it is inhibited. Since if that's not the case, then this operation will not be allowed. If you do change this, the original IP address will still be usable until the device is reset. So now we're going to take a quick tour of the SwiftE Web Connect interface and look at all the key components of the interface. So to do that, we're going to go online. We'll use that IP address that we just looked at, 192.168.140. I'm already logged in here. There will be a password. The first time you get this, you have to create a password. I already created mine, so I'm in here. We are in run mode, so it's waiting for a trigger. In program mode, you have free running data. So we'll put the controller in program mode and log in. So this is the home page that is presented immediately after login. It's dominated by a real-time representation of the data captured by the device. Below the representation is the range and intensity switch, where you can change from range to intensity and back again.
So, Chris, that's looking down into the box, right, Chris? You're looking down into...
Yes, this is the... that's my floor, and that's inside the box.
Yep, okay.
Okay. Below the range intensity switch is a scale bar, which allows us to control the representation as displayed. It's important to note that the colors used for display do not affect the measurement in any way. So closer sensing is represented by deep red, and further away sensing is represented by a deep blue. And you can change that to, I guess, whatever you like. The top bar up here indicates the mode that we're in here. You have access to device settings, where you can change the IP address. You can save and restore device configuration, perform firmware upgrades, and carry out general device maintenance. To the right of the representation is the template manager, where any existing templates can be activated or edited, and new templates can be created. So I'm gonna delete my templates that I have here so we can create a new template. Clicking Create New takes us to the template editor where we can begin to place virtual sensing zones. So you can take a circle here, and what this does is this averages all of those laser distance measurement points and gives you one reading. So and you can place up to 64 of these on this representation right here. So we can take a circle here. I'll show you what it looks like if you put a box in here. You got a white box and a brown box. This black spot here, that represents that the sensing points are beyond the signal threshold or saturation. So to fix that, we can turn the illumination power down, and that should fix that, and it does. I just want to make another note here, too, that if you turn your illumination power all the way up, this is your infrared light, this will heat up the device. So you should keep this as low as possible. Another sensing zone you can create would be a polygon. So you can draw around the perimeter of a device like that. Activating the virtual sensing zones instructs SwiftE to measure the distance to each zone. So you see we have 78 centimeters to the base of the box, 71 or 72 centimeters to the top of this box, and 70 centimeters to the top of this box. Once I'm happy with this template, I just click Save, and I give it a number and a name, and I click Save. Note that the icon here indicates that this is a distance-based template. So now we're going to use this template as a basis to create another one. So we will edit this, and this time we're going to make a height-based template. So I'm going to get rid of these virtual sensing zones, and I'm going to switch this to height. And you see I get an alert here that says remove all products from the scene and click apply. I'm going to go ahead and do that. Okay, and I'm going to place virtual sensing zones where I'm going to put a couple boxes. Very easy to do. When I activate these sensors, I have to oh, there's nothing there. So it's showing 0 centimeters, which is correct. So if I put a box there, now it's going to give me 8 centimeters to the top of the box rather than 70 centimeters to the top from the device. So when I save this, I'll give this a different template number, call it 2, and we'll call this one Rexel box height. Okay, so now I have 2 templates in my template manager. I can toggle between them by selecting which one I want, and it'll measure. It'll have my virtual sensing zones placed accordingly. Note that when I toggle between them, I have an alert on my interface that shows which template is active. Okay, so as your controller is in program mode, this is allowing SwiftE to be in edit mode for free-running data delivered directly into the controller without requiring a trigger. The data is live now. If I'm in program, or if I'm in run mode, which you will be in most of the time, it's going to require a trigger. So here, this is what it's looked like. I'm toggling between my distance template and my height template. Okay, so we're going into Studio 5000 now. You see I have an application here. I have basically nothing in it except for my controller. I have a 1769 L36 ERM Compact Logix controller. I'm going to show you how to add SwiftE to Studio 5000. So what we're going to do is we're going to right-click Ethernet, select New Module, and we can search for a module by searching for 3D. We can search for Swift. We can search for Odos, or we can just change the filter to 3D sensor and select it. So creating the device brings up the add-on profile. In this case, it's a very simple AOP where all we need to do is name it and type in the IP address, which was 40. This is the default IP address. From here, you can also change the requested packet interval. So the The default is 20 milliseconds. You can change this anywhere from 10 milliseconds to 1,000 milliseconds. Pressing OK generates the controller tags. We'll take a look at the controller tags in our organizer. Our output tags are created. Our output tags such as template to use and trigger are your most important tags. We're going to add these to our watch list. That, and then we are going to download this program to the PLC. This takes about 20 seconds or so. Make sure we got the correct communications path. So these other output tags here, illumination pause, it's recommended to keep this at 0. This will inhibit the illumination. So this was only used really if you have several 3D cameras that are next to each other so that the infrared illumination doesn't interfere with each other. Web Connect enable. This is also during normal operation, this will be at 0. What this does is the intention is to support inline testing and debugging during device implementation. This will allow free running data rather than requiring a trigger. And then you can reset your trigger counter and then clear it. This will clear all the input data in case it's required to clear data between measurements. Okay, so from here, now that we are, let's see, are we online with the controller now? I have an error. Oh, I just need to all right, so I can't go online, but we could take a look at the input tags here. So we have the status. The status is going to be 0 is going to mean OK. So right here, this means your measurement is OK. 63 means your measurement is in progress. 64 is a warning, and 128 is an internal error. So those are going to be your 4 statuses. Connection faulted. This will be 0 and 1 when connected. If the device is lost, your input tags will show you your template in use, number of virtual sensing zones in that template, a counter for your number of triggers, and then 4 parameters for each one of your virtual sensing zones. So your data will be your actual distance. Your status will be 0 if normal, or 1 if it's out of range. And then used in template, this will be a 1 if the virtual sensing zone is present, and 0 if it's not, and the type here. So this will be 0 if this is a distance-based virtual sensing zone, or 1 if it is a height-based. So let's see, reference tag is undefined, operand XIC when. That is giving me this problem. So that's basically it. That's how you connect the device to Studio 5000. I'd like to show you this device if I can online so you can see some more. We're still early. We have a lot of time here. SwiftE. Let's change that.
Chris, were you going to show the HMIs?
Yeah, I just want to go online with the controller.
Okay.
See what the problem was, John? I had SwiftE as my tag, but when I created the device in my controller tree, I named it Swift. So my tags weren't finding the device. So now we're online with the controller here. So now I just want to show you a very simple way to implement checking for presence or absence or layering using the SwiftE configurable camera. So I just want to go back to the device to show you what we're looking at here, and then what it looks like in the controller. So we select Rexel box height. We have 8 for a height of virtual sensing 1000. So we go into Studio 5000. We can look at our input tags, and you see the virtual sensing zones. We have 4, a counter of 3. Data for virtual sensing zone 2 is 0. If we go into our program that we made here, called check presence, so all we have here is a separate rung for each virtual sensing zone. The first instruction wants to tell us if that virtual sensing zone is in fact in that template. So we see virtual sensing zone 5 is not, so it's not energized. The first 4 are. The second function block we here have is a limit instruction where we created a reference low. I selected 5 because your background will usually show 0 or 1 centimeters, and a reference high because your product should not be higher than 15. So our data from virtual sensing zone 1 is 8, and that's live. So if I put something on top of virtual sensing zone, that'll change, and our output will be energized if that instruction is true. So remember, in run mode, we require a trigger to change data, and in program mode, we have free running data. So here, all the other 3 virtual sensing zones are 0. We can check that here. You can put stuff. And now that we're in run mode, this will not update either until we issue a trigger. So we have our zeros and our presence is off. So this is a very simple way to implement checking for presence or absence or overlapping. So from here, I just want to show you one more thing. We'll use a different program that'll take input tags from an HMI screen. And I want to show you some example HMI screens that you may possibly want to use to display data from your 3D sensor. I'll download this other program here. And then while that's downloading, we'll pull up Factory Talk View, or View Designer, and then we will emulate this Panel View 5000. Okay, so this is emulated Panel View 5510. So this is an example screen. This is kind of cool because this will actually show you where you can display the data from all 64 sensors at the same time if you would like on that same screen. You can have a trigger input that goes to your controller from here to take new measurements. You could display your data as sensor bars if you wanted to. I like switching back and forth so you can see what this looks like on both ends from the camera itself. And I'm putting boxes in and out of here so you can see the stuff change. And it's waiting for a trigger, so we'll issue a trigger, and that changes just like that. And I added a box there. So we took a new trigger, we have a new measurement here, and our panel view gives us that answer. Another example would be a fullness. So we set full at 15 centimeters. I have two boxes on top of each other. So for something like this, for fullness, we would use the polygon virtual sensing zone, and we would draw around the perimeter, and we would use this to give us fullness. So I just took a box off of a virtual sensing zone, we could trigger, and say it's 53% full. So these are a couple examples. This concludes my presentation here. Hopefully all of your wheels are turning about how you can integrate a 3D camera into your automation project. I'm gonna let John read off some of your questions that are in the group chat from here, and you can let me know what you think about everything.
Chris, that was great. As usual, you're very in depth. So just again, for those clients on the phone, the summary is the applications for this camera tend to be, as you saw, packaging, right? So palletizing, case packing, completeness, right? If accuracy, if you're having issues where your counts are off or they haven't put complicated kits together, with 64 different sensors, it's pretty powerful. And as Chris showed you, it's pretty fast in the sense that it's flexible and easy. But I wanted to make sure that, again, it's validation, right? It's a validation device. It's not there to measure details. It's more to validate. And that's where this camera application makes the most sense. Chris, we had one question. I think my friend Ben Casto answered it for Roger, but he just wanted to confirm the maximum distance is 6 meters.
That's correct. I'll add a little bit to that. At 6 meters high, that's going to make our sensing area a little bit larger. So the width of our area that we will be sensing at 6 meters will be about 4.8 meters wide and about 3.6 meters tall. So we'll have a much larger area to sense if you were to place the device that tall. As a rule of thumb, the width would be 0.8 times the height, and the height of your sensing area will be, I should say, the y-axis will be about 0.6 times the z-axis for the area that you can sense.
Okay, Roger, another question, and Roger, if you want to unmute yourself too, because I'm interested to know the answer here. Can I get coordinates from this? I'm not sure, Roger. Do you mean? Do you want to clarify that, Roger?
Yeah, I think I got the answer, but what I'm looking for is a device like this to give me. So I've got an application. We do liquid filling machines, and we have an application where 4 barrels come into place. And I'm looking for the location of the bung hole of the barrel so I can automatically fill to that location. But
so Roger, these are not going to give you X and Y coordinates at this current revision, and I don't know if that's a future something that they're going to add to this or not. I want to make a point that this is giving you distance measurements, so your sensing points that are directly below the camera will be more accurate, whereas the sensing points on the perimeter will be at an angle, so they will be slightly longer. So to remedy that, using the height-based template will be more accurate because it sets all of those base levels at 0. If you wanted to find coordinates, you'd probably place a second sensor around the side of your target.
Yeah. So I'm looking for is voids in the surface of the barrel, right? So there would be 4 barrels there. I would know that I would have 4 barrels, and I'm looking for a void in that barrel.
If you are going to be, yes, you can use this to place virtual sensing zones in the voids, and if that's giving you a high reading, or if it's within your limit in your program, then you can absolutely detect that with the 3D camera.
Yeah, the problem is I don't know where the void is going to be located.
Yeah, I was just going to say that next. It'll be a lot more accurate if you can define where those barrels are supposed to be.
I know about where they're supposed to be. The problem is I don't know where the void is, and that's my whole issue.
Okay.
So the void could technically be in a circumference on that barrel, right? But I don't know where in the circumference that it would be.
Well, if you want to try it out, or I'd be happy to take a look at that with you offline and dive into it a little bit further if you want.
Okay. That'd be great.
So that's it. Just the one question then. I think we're all set here.
Yeah, I don't think there was, oh, Greg has a question. Oh, Greg's just saying, for Roger's sake, Cognex camera is possibly a better option.
This has been Casco. I'll just mention that this is a huge field of view compared to other sensors. A Cognex camera has usually got to be within a foot of something. So 6 meters is huge.
Thanks, Ben. If anyone else you don't have to necessarily type a chat, but if you had any questions, either Rexel people or any of our clients that are on the phone still, they want to ask Chris a question or the group. Again, if you want more information on it, and we did record this, so it is available to go back and look at it, but if you want Chris to call you individually, he can, and he's willing to talk about your application. So Chris, thanks again. I know this was a lot he put together. Appreciate it. If that's it, it's a wrap. Thank you.